Hey everyone, welcome back. Today I want to work on a couple of the problems from your worksheet. We'll do number 6 and number 7 from worksheet 15. So these ones actually have us calculating an equilibrium constant. And I said I won't actually on your exam make you calculate an equilibrium constant or make you calculate anything from an equilibrium constant in this class. But I do want to still have you do that on the worksheet, and I'll sort of explain why as we go through this. So let's go ahead and see what it takes to calculate an equilibrium constant here. So the problem says we've got this particular chemical equation, and it's PCl5 in the gas phase reacting reversibly to form PCl3 and Cl2 gas. So this is just a bit of a decomposition reaction where PCl5 decomposes, or they can recombine into PCl5. So the problem says at equilibrium, so once these are allowed to react and come to equilibrium, then PCl5 will be at 1.0 molarity, PCl3 will be at 0.10 molarity, and Cl2 will be at 0.10 molarity. So we set up an equilibrium constant expression this way. We always put the concentrations of the products on top and the concentrations of the reactants on the bottom. So it's the concentration of PCl3 times the concentration of Cl2, because those are the products. And when I say concentration, I mean molarity, divided by the concentration of PCl5. Remember the brackets around it mean molarity. So molarity of PCl3 times the molarity of Cl2 divided by the molarity of PCl5. So to solve this problem now, literally all we need to do is plug in those numbers. And you're going to be totally shocked when I say that, but we actually plug them in unitless. Oh no. There's reasons for that, but they're not really worth going into right now. So what we do then when we plug them in unitless is we take just the numbers and just literally plug them in. 0.1 times 0.1 for Cl2 divided by 1.0. And we get 0.010 for 2 sig figs, and that's our answer. That's our equilibrium constant for this reaction. So to see what that number means, and this is really why I want to make the case that this was a worthwhile process, is you see that you took the numbers, the molarities for the products, and divided them by the molarities for the reactant at equilibrium. And looking at them here, you can see that these are smaller molarities than the reactants. So we would say this reaction favors the reactants there. At equilibrium, there are more reactants present than there are products. You can see that since we plugged in smaller numbers on top and bigger numbers on the bottom, that this small, less than 1, equilibrium constant is for a reaction that favors reactants. So first off, you can see you've sort of proven to yourself that a small equilibrium constant favors reactants. The second thing we can do is we can talk a little bit here, just jump to talking about Le Chatelier's principle. So you can see how this works. This equilibrium would always need to be in this ratio. So if we, let's say, went ahead and doubled or some other amount, let's say we added some amount of PCl5, say we add 1.1 molarity. So now that would be a total of 2.2 molarity after we've made that change. Well, if you plug that in, that would not give this number anymore. So this would naturally need to change. This reaction would naturally need to do what we say, shift right, or unreact some of these. So maybe subtract 0.1 molarity and add 0.1 molarity over here, so that now we're back to 2.1 molarity over here and 0.2 molarity over here. And that now again would give us a similar ratio to this. And that wouldn't be the exact ratio, but you can see what we're what we're getting after here. And I don't know, my adding skills went really wrong. 1.0 plus 1.1 should be 2.1, which would make this 2.0, 0.2 and 0.2. And that would keep shifting back and forth until we've reestablished this exact ratio that would recalculate this exact number. So even this, what I've given you is kind of a quick idea, but it's not the exact numbers that would recalculate this ratio. So we can go a lot into that and actually do the calculation, but we just want to actually infer really quickly here that if you add reactant, like we did over here, the shift must happen to the right to reestablish the balance between products and reactants at equilibrium. There you go. Now let's try another one. This was a very simple example, and the next one's not so terribly hard, but let's actually go on and work on problem number 7. I'll flip this over. So find problem number 7 here on this page, and I'll get some paper to write on. All right, so this is a very generic reaction. This isn't reactants that we know of. This is just A's and B's and C's, but it's the same process. We just need to look up here in our problem and see what the molarities are. The molarity for A is 0.25 molarity. The molarity for B is 0.10 molarity. And the molarity for C is 0.45 molarity. And we need to write the equilibrium constant expression. And really the only thing different here when we write the equilibrium constant expression is we're going to put the molarities of the products on top and then the molarities of the reactants on the bottom. But since this one has coefficients other than just one, there are 2 C's on this side, so we would need to put 2 C's on top, or just make it squared. So the coefficients actually become exponents in the equilibrium constant expression. Then there are 2 A's over here, so we would need to put either 2 A's on the bottom, or again, just make it squared is the natural way to do that. And then there's 1B, so we need to put 1B on the bottom. So to calculate this equilibrium constant expression, we're all set up. We still just need to plug in the numbers. 0.45 squared divided by 0.25 squared and 0.1. You'll plug that all into your calculator. You'll get 32.4, and to round to correct sig figs for your final answer, you'll get that the equilibrium constant is equal to 32. And that's it. Thanks for sticking with me. See you in class.